All right, let's take a journey. We're going to dive deep, right into the heart of a black hole, past the point of no return, to explore one of the wildest and honestly most beautiful ideas in all of physics, the Planck Star.
It's one of the biggest questions out there. For decades, the answer has been this huge point of conflict between our two best theories of how the universe works. So what really happens when a star collapses under its own gravity and just keeps on collapsing?
Well, according to Einstein's theory of general relativity, you get a singularity, a single point where all that matter gets crushed down to infinite density. It's a place where the laws of physics, as we know them, just stop working. It's basically a mathematical dead end. But that's not the whole story. There's this other theory, a competitor, called loop quantum gravity, or LQG for short. And it has a completely radical alternative. It suggests that if you could zoom in far, far enough, you'd see that space-time itself is made of these tiny, indivisible chunks. And that one little idea, it changes absolutely everything. And this brings us to something called the quantum bounce mechanism. So forget infinity. Loop quantum gravity actually predicts that the universe has a built-in safety net that stops a singularity from ever forming in the first place. Let's break down how this is supposed to work. So this is where the two theories just completely part ways. General relativity on one hand says the collapse goes on forever, but loop quantum gravity basically says, hold on, not so fast. It proposes that the grainy quantum nature of spacetime itself pushes back, forcing all that collapsing matter to rebound in what they call a quantum bounce. And this bounce happens when matter hits the absolute cosmic speed limit for density, Planck density. That number on your screen, it's so ridiculously huge that it's almost meaningless to try and imagine. But in physics, it is a hard stop. It's the point where the very fabric of spacetime says, nope, you can't get any smaller. So this whole process creates something brand new. You've got matter falling in, it gets squeezed down to that absolute physical limit, and then space-time itself pushes back. The result isn't a singularity at all. It's a stable object, a Planck Star, a tiny, unbelievably dense remnant sitting right at the heart of what we call a black hole. But the birth of a Planck Star, that's really just the beginning of the story. What comes next is a waiting game on a scale that is just staggering. It's an unimaginably long goodbye. Just look at that number, 10 to the power of 90 years. That's a 1 with 90 zeros after it. That's how long a Planck star, born from a black hole the size of our sun, is predicted to just sit there and exist. For comparison, the entire universe is only about 10 to the power of 10 years old. Yeah, to put that timescale into perspective, our entire cosmic history from the Big Bang until today is just an infinitesimal blip on this timeline. Even the predicted heat death of the universe, trillions of years from now, is basically a rounding error. The Planck star's life plays out in an era so incredibly distant, it might as well be another reality. So what happens at the very end of this cosmic wait? Well, that quantum bounce finally completes. The Planck star, which has been sitting patiently inside the event horizon for eons, finally inverts itself and explodes outward as a white hole, releasing all the matter and information it swallowed back out into the universe. Wow, right? That sounds like a pretty spectacular event. A signature prediction of loop quantum gravity. So, can we see them? Well, this is where this beautiful theory kind of becomes a ghost in the cosmos. Let's talk about why we will almost certainly never, ever see one. So, scientists actually classify these kinds of hypothetical objects by how detectable they are. And Planck stars are in the highest tier of impossibility, tier 4. And the reasons are pretty fundamental. First off, that final explosion isn't going to happen for eons. And second, any signals it might possibly emit are at a frequency that the universe itself is basically transparent to. The barriers to detection here are absolute. Any radiation or gravitational waves, they'd be at the Planck frequency. That's a frequency so high the universe doesn't even interact with it. And that final white hole explosion, the timescale really says it all. We are trillions upon trillions of years too early to the party. And the hard reality is that right now, every single observation we have of black holes, from the gravitational waves they create to those incredible pictures of their shadows, it all perfectly matches what general relativity predicts. We see absolutely no hints of these weird quantum effects. Okay, so if we can't ever test it,
What's the point? That's a fair question. Well, the idea of Planck stars forces us to ask some really deep questions about what science even is, about theory, and about proof. This is what physics at the very edge looks like. Just to put this into context, physicists are hunting for all sorts of exotic, weird objects out there. Some of them, like dark stars or boson stars, we might actually be able to test for with current or near-future tech. But Planck stars? They're in a completely different category. Their biggest barrier isn't technology, it's time itself.
And this is the real tension here, the core of the problem. You could argue the Planck star is the signature prediction of loop quantum gravity. It's this beautiful, elegant solution to the singularity problem. And yet, that very elegance makes it impossible to ever prove. And the stakes here are just enormous. If, and it's a huge if we could somehow see a Planck star, it would be a total make-or-break moment for loop quantum gravity. It would be the definitive proof it needs. But because we can't, general relativity stays on top, and other big ideas like string theory are completely unaffected. And maybe that's the real takeaway from all of this. We usually think of the limits of science as being about technology, right? If only we had a bigger telescope or a more powerful particle collider. But Planck stars suggest a much deeper, more profound limit: time. A perfect theory might have predictions that are completely unprovable, simply because we don't have the cosmic patience to wait around and see them happen.
Which leaves us with a really fascinating and maybe even a little unsettling question. If a theory makes a prediction that is fundamentally impossible to test, not because our tech isn't good enough, but because of the lifespan of the universe itself, is it still science? Or has it become a kind of mathematical philosophy? Something to think about.